Example 4. Use the following diagram to give an equation describing the wave in the diagram. Now, to begin with, let's point out, we just want to remember y equals a, the amplitude, times sine, the function that allows us to have periodicity, allows us to have oscillations occur algebraically, kx minus omega times time. So x, the location that we are on the wave, t, the time that we're looking at the wave, omega is the factor that allows us to handle the fact that periods cause repetitions, k is the factor that allows us to handle that wavelengths cause repetitions. So to begin with, we know that the period is equal to 0.02 seconds. And we know that amplitude is equal to 0.5 meters. Okay, great. What is this here? Well, that is not equal to the wavelength. Remember, if we look just to the right of this point, and we look just to the right of this point, we should see the exact same thing. We don't see the exact same thing. It's going down over here. If we go over here, though, we will see it. And because it's a sine wave, because it's evenly spaced out throughout, we know that 3.5 meters isn't going to be the wavelength, but it's going to be half the wavelength because it's in one of the dips. So wavelength over 2, so that means that our wavelength is equal to 7 meters. All right, so there's all the data that we wind up needing. Now we want to solve for what k has to be. K is equal to 2 pi over lambda, so k is equal to 2 pi over 7. Omega is equal to 2 pi over the period. Oh, by the way, k. We're throwing around k a lot. I never mentioned this, but k is not the same k as when we were dealing with springs. It's a different k. We're using it to mean a totally different thing at this point. The k that we're using in this stuff is different than the k we used before. Just like how little t and big T don't necessarily mean the same thing. We can even wind up using the same letter for different things, and we have to know contextually what we're talking about. Sorry, I made that assumption, but that's actually a really important thing. You don't want to get confused and think that springs and waves necessarily have to do with each other every time. It's not that same spring constant we were talking about before. Totally different use of k. Anyway, back to this problem. So omega is equal to 2 pi divided by the period. So if we know what the period is, 2 pi divided by 0.02 seconds, and that will wind up giving us 100 pi. So simple as this at this point, we just plug in all of our numbers. So y is equal to, that amplitude was 0.5 meters, times sine of the numbers 2 pi over 7 times x minus omega, 100 pi, times the time that we're looking. And that right there is our answer. Simple as that. So we just want to be able to analyze the diagram, and one of the most important things is to pay attention to the fact that wavelength has to be not just some distance where you get the same point, but same distance where you get a point that means the exact same thing. That if you look just a little bit further on and a little bit further behind, you're going to see a full repetition. It's not just the same point, because the same point occurs at any horizontal thing, right? Except for the very tops and bottoms. So these pairs of points aren't enough to determine a wavelength. What you need is to reach a little bit farther and look here. The very top to top, because tops themselves only occur once every wavelength, whereas middles occur twice. Same with bottom. So you can go from the bottom to the bottom and the top to the top, and that's normally the easiest thing to measure. But if you're measuring from the middle to the middle, this isn't enough. You need to also go to here. Okay, great. I hope you enjoyed that. I hope it made sense. Waves are a whole bunch of big ideas, but we're going to dip our toes in it and get some understanding of how a lot of things in this world work. All right, see you next time.